So kami naman nag-assign the gym. And then
All right, so we're going to go ahead and get started just a touch early. Richard has gone back to chess to do some work on getting beam lines ready for tonight, so I'll be, I don't know, sharing this half of the course, I guess. So this is now kind of what we call the advanced technique section of the course. So in the morning, you heard all about scattering profiles, how to prepare samples for experiments, and then once you've taken some data, the very first things to look at to make sure that you've collected your data. So now the second half is kind of aimed at, assuming you have good data, what do you do then? With the exception of BioSAXS, which is now kind of a standard technique, which maybe should get pushed around. But you'll get to hear about reconstructing three-dimensional shapes, how to use advanced experimental techniques to get more out of your samples, and some really exciting new techniques that Richard has alluded to for getting electron density. So this is Tom Grant, who's at the Woodland Institute at Buffalo, right? I think you're now a research professor, so he's going to tell us all about envelopes and various other things.
Yeah, so what we've done in years past is I've had sort of a introductory version of this. So what we're getting into now is like modeling, like how we're going to do 3D modeling of things. And so in the past, what I've done is sort of two different sections. So more of an introductory section, and then later in the day, an advanced section of modeling. But what I'd like to do is later today talk to you about the density reconstruction stuff that I came up with. And so what I've done is I've kind of now, I figured this information is still useful, so I've jammed it all into one big talk. So I'm going to skip a whole bunch of slides, but they're in your packets, so they're in your slides, just so that if you want to know what's available, you can skim through them. I'll try and skim through them, but I'm effectively just going to skip over things that I don't think are, as useful for an introductory talk. And then, if I get bored, I'll just stop. So, okay. So to start with, these are some references that I think are very useful. A bunch of them have been mentioned already. One thing I want to add is this website. So this is a really nice website if you do a lot of different types of small angle scattering. This doesn't just include biological small angle scattering, but has a bunch of scattering software for material science or other applications. So if you're just interested in the general concept of small angle scattering, you can get a lot of information about software there. Okay, so some of this to start with is going to be somewhat of a review, but I think it's always useful to get different explanations of it. So this is what we call a molecular transform. So a molecular transform is a three-dimensional view of reciprocal space. So if you took the Fourier transform of the electron density function of your molecule, you get something like this, but in 3 dimensions. Okay, so this is a 2-dimensional slice, and so what we have is we have at small angles, we have this big bright blob, and all of these sort of, as Richard mentioned earlier, a speckle pattern is what we typically call it. And so these are fluctuations at higher resolution that if we could actually get this from an experiment, we'd be able to do an inverse Fourier transform, so we knew our phases, and be able to reconstruct the exact electron density function. And so this same basic physics is what we're using in solution scattering. And so we start with our molecular transform. And to give a comparison for those of you that are familiar with crystallography, what happens in crystallography is we have Bragg sampling. So we have our molecules ordered in this 3D lattice, and that causes us to have these specific discrete points sampled throughout this pattern, and that ends up sampling the underlying intensity profile. Okay, and so this information is what you actually get when you're looking at a crystallographic, reflections. And building this up in 3 dimensions allows you to go ahead and solve the structure. The same basic physics applies to solution scattering, where we start with our molecular transform, our single molecule diffraction. But because we're doing small angle scattering, we're just going to look at this bright blob at the center and not be concerned with these wider angle scattering terms. And so we look at this, but this is obviously not what we get from an actual scattering experiment, because in our experiment we have molecules tumbling. And so each one will scatter with a different angle, or a different orientation relative to the beam. And so we end up having an isotropic scattering profile. And so effectively, think about this in 3 dimensions. This is actually a 3-dimensional function. It's just spherically symmetric. And so all the intensities get averaged, and we're taking a slice through that from our detector. So this is our basic SAXS setup. We have our X-rays hitting our sample with the molecules tumbling randomly in different orientations. And because of that, we end up with this isotropic scattering profile. And because it's isotropic, we can azimuthally integrate at each different Q vector, and we end up with an intensity profile, a 1D profile of intensity versus Q. And so this can tell us information about our particles. So it's all low resolution information because we're at small angle. Because of that, we can kind of think of this in terms of reciprocal space, that larger particles will scatter at smaller angles and smaller particles will scatter at larger angles. And so we can analyze this profile to yield information about the size and shape of these particles in solution. So these are a bunch of the different types of things. This has all been going over, so I'm going to go ahead and skip it. So here we have how we actually get our experimental profile in a very, very, very simplified way. The intensity that we get on our detector is a product of the form factor of the particle, which was the slides I was just showing, this isotropic profile from our molecular transform. And it's multiplied by what we call the structure factor of the particle in solution. And so the form factor gives us intra-particle interactions, so the atoms within a molecule. And the structure factor term gives us information about interparticle interactions between molecules. So things like if molecules are repulsive or attractive, you see that in the structure factor term. Now, most of the time, what we're actually after in our experiments is the form factor. So we want this term to be 1. And so for that, we need a monodispersed solution that is neither attractive nor repulsive. And so this is how that actually comes into play. So for attraction up on the top here, we have our form factor, and we have a structure factor that if it's attractive, it's positive, or it's greater than 1 at low Q values. I should have my axis. This is Q on the x-axis. It's greater than 1 at low values, and so this causes this to sort of increase at low values. And for repulsion, we have the opposite. We have slightly less than 1 at low Q values, which causes sort of this downturn. And so we can analyze this and determine whether or not we have attractive or interparticle interactions through a Gagné plot. And so this was mentioned before, so I won't go into the derivation. But effectively what this means is that we can plot the natural log of intensity versus Q squared and end up with what should be a straight line based on these sort of first principle approximations. So this is an example of a Gagné plot, a nice Gagné plot. I think this is for lysozyme that scatters with a nice Gagné linear region out to high angles. You can see that it's a nice flat line. And we can actually, from this line, then get information about the radius of gyration, and the y-intercept gives us information about the molecular weight of the particle. However, for something like this, where you have this wide curvature, this sort of positive curvature, we kind of call it a smile, and the smile gives us information that it's attracting to itself, and or there's aggregation in the solution. If you have repulsion, you'd have something where it's just the opposite. You'd get sort of a frown, and that would tell you that you're getting repulsive effects in your solution. And so if there's aggregation, you're going to get a effective radius of gyration that's larger than what actually it should be. And if it's repulsive, you're going to get a radius of gyration that's smaller than it actually would. So one of the problems with the assumptions of the Gagné plot is that it assumes everything is sort of this Gagné type particle. And so a lot of particles are not necessarily these Gagné type particles, in particular things like rods. So what we typically use is a Gagné range of where Q times Rg is less than 1.3. So everything down here. You can see that in the Gagné plot below Q times Rg of 1.3, pretty much everything is linear, except for a rod, which a lot of times they say less than 0.8. And that above 1.3, these basic shapes deviate from this Gagné assumption. That's why we only look at the small angles. The very small angles for Gagné plots. So this gives you an idea of what range we're looking at. And so one of the things you have to think about in your experimental setup, yes?
If you did have a rod and you were looking at its Gagné plot, would just the right half of the plot near 1.3 be smiling, and then the left part would be on the line? Or?
Yeah, so it'll get more linear the closer to 0. So that's the idea of your if you're thinking about the derivation of this. This is an exponential, so it's sort of assuming Gaussian kind of. This is a kind of a Gaussian form, and so it gets more linear the closer you get to 0. Is where because it's an approximation as q goes to 0. So the approximation gets more accurate as q goes to 0. So it'll be, you're right, it'll be more accurate, more linear in this region than in that region. But
so you can differentiate between a rod-shaped distribution and an actual aggregate, just based off of how close it is to the straight line at 0?
I would not necessarily say you could distinguish between them, because unless you knew ahead of time that it was rod-like, you wouldn't necessarily know if it's aggregated or elongated. It's
So
kind of one of the.
So if you get a smiley face, is it safe to assume that you always have aggregation, or can, like, do people automatically ask, like, is this just a rod?
Yeah, it's hard to tell. You can't really tell the difference unless you do some kind of secondary characterization, which was a lot of what Kushal was mentioning earlier.
And what you can do is you can bring in your Qmax and see if it flattens out, right? Aggregation is going to show deviation across the entire range, even as you bring in Qmax, whereas a rod will get linear. That's typically speaking, as you bring in Qmax lower. So.
Yeah. So in other words, he's saying if you collected a lot more data, a lot more sampling down at lower Q, you might be able to distinguish that. All right. So this is just an example of make sure you collect enough low Q data. Okay, so here we're going to talk about the pair distribution function. You've seen this. There's a factor of 2 missing there, so believe the other equations. So you can calculate the radius of gyration from your pair distribution function. This is particularly useful if you have particularly large particles. The reason for that is because for larger particles that may only have a few data points in the Gagné region, this uses all of the data points through the entire scattering profile. So you're able to have a lot more data points to determine your radius of gyration. It's also less sensitive to interparticle interactions because it's using the entire curve, where the interparticle interactions are most obvious at the low Q region, which is where Gagné approximation lives. So this is an example of some of the different types of P of R distributions that you can get from different types of shapes. So you sort of get this, Gaussian looking thing for a sphere. If you've got some kind of dumbbell thing, you'll get 2 peaks, because this peak gives you information about the cross lobe distances, whereas this larger peak here gives you all these sort of shorter distances inside each one of the lobes. You can see a rod has sort of this left skewed distribution, and a disc sort of gives you this wider P of R distribution. So just from the P of R distribution, you can get some information about your particle.
The two circles are 2 discs?
No, this is 2 spheres.
2 spheres.
This is potentially one area where you might be able to distinguish between a rod and aggregation, because a rod will sort of have this large peak left skewed and then gradually fall, whereas aggregation could be like, this and then just tail out. And so a lot of times that's what you'll see is these long tails, and I'll show some examples of that. So when you're actually practically determining your pair distribution function, you got to be careful that there's a lot of assumptions that are made in the pair distribution function. If you just calculated the raw pair distribution function directly from the scattering profile, you'd end up with some crazy oscillations in it, and that's because we don't collect an infinite amount of data. We truncate our data to some edge of the detector, some maximum Q value, some highest resolution, and so this causes these ripples in our thing, and so we use some smoothing in various implementations. For example, in genome, this is called alpha. And so a bigger alpha means a smoother profile. I think I've got some examples of that here. So you can see like an alpha will smooth out your profile, and you can determine Dmax and give you a nice smooth pair distribution function. But the caveat to that is that if you over smooth, then it no longer fits the experimental profile. And so you need to balance those 2. Okay, so one of the things you can get from pair distribution function is the maximum dimension of the particle. And so if you want to get Dmax, you can, typically what I do is I say, well, let's start with a large value, say, I don't know, 150. You can get a rough estimate of what it is from the radius of gyration. It's usually about 3.5 times Rg, roughly. I mean, it depends on the shape of your particle, but usually I start at a large Dmax relative to what I think it probably is. And what you'll notice is that at a large Dmax, it sort of just oscillates around 0, and you can kind of get an idea. So say Dmax here is 100. Now, if you put in too short of a Dmax, it sort of abruptly falls, and you want this gradual fall. That's typically what particles do. And so from that, you can get a relatively decent error of a decent idea of Dmax. But there are large errors in Dmax. You can see just from the fact that this decays gradually, you could probably choose anything between, I don't know, 85 and 105 and they're equivalent, right? So there's a large degree of error in determining Dmax. If you also think about it in terms of what Dmax means just practically, if you have, I don't know, a lysine on the end of your protein that's flopping around, for some of the particles where it's imaged here and it's compact, it could be 5 or 10 angstroms smaller than if it's fully extended. So everything we get in solution scattering is an ensemble average of all of these data. Okay, so this is just one point that I want to make about understanding the role of Dmax. So Dmax is actually a pretty important parameter in determining things like the pair distribution function and just understanding what it's giving you in terms of the signal in your profile. So what we use, the fundamental theory we use for being able to extract the pair distribution function is called Shannon information theory. And so this states that an exact continuous signal, sort of the smooth fit to your data, can be recovered from the discrete sampling of that signal, which are the individual data points, provided that you're sampling the profile at least 2 times the highest frequency present in the signal. So in the case of SAXS, that highest frequency, remember we're dealing with reciprocal space, is the maximum particle dimension, or corresponds to the maximum particle dimension. And so the highest frequency is, remember it's twice that, so it's 2 pi over 2 Dmax, which ends up being pi over Dmax. Okay, so that gives you your sort of what we call a Shannon channel, or the width of sort of the highest frequency in your data. And so this gives you information about the number of pieces of independent parameters, or independent pieces of information in your actual scattering profile. So if you took the whole range of your data, Q max minus Q min, and you divide it by the width of the Shannon channel, that tells you how many Shannon channels you have. And typically, you only get something like 10 to 30. This depends on the size of your particle, what your experimental geometry is, but typically something like 10 to 30. So think about this for a second. This says that not only is SAXS a low resolution technique, it's also a low information technique, because there's only some 10 to 30 independent pieces of information in your scattering profile. So it's actually amazing to think that even at low resolution, we're able to do things like rigid body modeling or determine ab initio envelopes and get shapes when there's only 30 pieces of information at best in these profiles. It's really kind of fascinating. This I mentioned. This is from that Jacques and Truella paper that I mentioned earlier. A nice resource to give you an idea of how sample quality affects data analysis. And I think you've heard a lot of this, so I'm going to get into the modeling stuff because there's a lot to get to. Okay, so let's start with envelope reconstruction. So one of the things that you'll do initially when you go through tutorials tomorrow in terms of shape reconstructions with bead modeling, or a lot of the different modeling tools, is you'll go into Primus or into Raw, and you'll run Genome or BIFT or something to calculate the pair distribution function. And when you're running Genome, you'll get your pair distribution function, and then you'll save that as a genome file. And you use that for running the bead modeling programs like DAMF or GAS4 or DAMN. And so it's really important to make sure that when you're doing that your fit to your scattering profile actually matches. So you don't want to over smooth your pair distribution function because it affects your reconstructions. So the way that these programs work is that they fill space with a bunch of beads, sort of this hexagonally packed, tightly arranged grid of beads. And they turn the beads to either be solvent or particle. And when it starts with a random configuration. I don't think it's entirely random. They have some kind of connectedness thing to them. But it's effectively random. And so the idea is they change one bead at a time to be either solvent or particle. And then they calculate what the scattering profile of that collection of beads is, and they compare it with your experimental data. And they do this millions of times. And they iterate, and they say, every iteration, let's change a different bead. And let's say, how well does the scattering profile match? And does it get better or does it get worse? And if it gets better, they keep it. If it gets worse, they throw that version away. And they try again. Now, it's not entirely like that because they use simulated annealing to allow for some incorrect selections. And the reason for that is because if you only went directly through this sort of gradient search where you're always getting better, you're going to get trapped in local minima all the time. And so it uses simulated annealing to sort of try and randomize some of this to allow for some incorrect, potentially worse versions of this, but that may in the future, when it goes through more iterations, get better. And so when you're running these programs and you see things like simulated annealing and temperature factors, that's all referring to effectively this allowing it to get worse with the hope of in the future getting better. So that's the basic idea. Now, it's not just how well it fits to the data. It also uses some real space restraints. And so, for example, if you just ran it with the idea of fitting the data, you'd end up with beads in lots of different sort of disconnected spots. And that's not good because proteins or biological molecules don't look like that. They have sort of a connected globular shape typically. And so it uses that information as additional restraints. And so we create a 3D model by kind of conforming to these physical restraints through the use of penalties. And so these bead modeling programs will penalize. If there's a bead way out here, it'll say, well, that's unlikely. I'm going to downweight that as a potential option. And so it adds these penalties. And so your fit to your data is how well your experimental data and your calculated scattering profile from your model fits. But it also has these penalties, and it comes up with a scoring function. And this is sort of how it goes through this process. And it was really these penalties and this whole thing that allowed this to work in the first place. That if you just have this part without the penalties, you can actually run this if you want to just test it out. You can turn off these penalties, set all the weights to 0, and you'll end up with some pretty crazy reconstructions. Now, every time you run this, you get a different reconstruction. The reason for that is because, as I said, you start with a random selection of beads. And so if you run it 10 times, you get 10 slightly different reconstructions. Now, the hope is that because it should be dominated by the information in the scattering profile, that most of the time at low resolution, they're similar. And so the idea is that if you run it a bunch of times, you can average them and get one that sort of has all of the features that are consistent among all of the different reconstructions, but throws away the features that are not common. So we call this a consensus model. So typically you're producing something like 5, 10, 20 ab initio reconstructions. You determine the most probable model, which is effectively the most similar. And you align everything to that, and then you see how different are all of the other models compared to that one. And this gives you an idea of how reproducible your reconstructions are. So for things, I think, I'm not sure, but I think Richard might have mentioned before the program Ambometer, which gives you an idea of how ambiguous your, almost like how complex your shape is based on the scattering profile. And so for things that are not ambiguous, things that are simple and easy to reconstruct, you'll typically get NSD values, which normalized spatial discrepancy is sort of a way of quantifying how similar different three-dimensional volumes are. And so normalized spatial discrepancy of around 0.5, and it says that there's good stability of your solution, it's unique, and there's not many different ways that you can reconstruct it. A moderate NSD is something like 0.7 to 0.9, and this implies spare stability. You might get some reconstructions that are slightly different than other reconstructions. An NSD value greater than 1 implies that it's very ambiguous and it's difficult. Now, this is not necessarily a reflection of the quality of your data. It's just a reflection of how complex your particle shape is. Now, sometimes if you have crappy data, you're going to get, bad reconstructions because it's not able to fit the data very well. But if you've got, even if you've got pristine data, simulated data even, if you've got a very complex shape, it can be very difficult to get NSD values that are low because it's just an inherently difficult structure to solve, to reproduce. One thing is this can give you some idea of flexibility because if you've got multiple conformations, it's difficult for the algorithm to reconstruct a single conformation that matches the sort of the ensemble average in terms of scattering. And so in addition to DAMAVER, you can use the program DAMCLUST, which will try and cluster these things together, and I think that's maybe one of the tutorials that'll be going over tomorrow. Okay, so now I want to talk about how aggregate, yes?
How big are the beads?
It depends on the size of the particle. So it determines this to try and, as a balance between speed of the program and sampling in real space. So, you know, you could have 100,000 beads, and each bead could be 1 angstrom, and it would take 10 days for it to run. So what it does is that I think it's typically like 10,000 beads, something like that, that it uses, and depending on the size of the particle, it'll fit the size of the bead to make it so that there's about 10,000 beads. So if you've got a 100 kilodalton particle, that's maybe a Dmax of, I don't know, 100 angstroms, it'll probably have 3 or 4 angstrom radius of the beads. So it's very coarse grained, typically. So aggregation will show up in different ways. So if you think about what aggregation is, for the most part, your sample is a single population, let's say. Say 90% of it is all a nice monomer, but then you've got some 10% of your sample is aggregated, which means it's forming these non-specific interactions that maybe are forming dimers and octamers and duodecahexamers or something like that that are super big and very large. And what happens is because those oligomers are large, those aggregates are large, they scatter much more strongly than the rest of the sample. So even having some small fraction, you know, 5%, 2%, 1%, can have a significant impact. And so that's the idea here, to give you an idea of how the purity of the sample is important. And so here we have some simulated data from lysozyme with just some noise added. And what I did is I took one of the possible oligomeric states based on crystallographic packaging. I think it was an octamer I used. And I said, if you had a certain percentage of octamer, how would that affect your scattering profile? Now the first thing you notice is that the only thing it's affecting is the low resolution information. And that's because most of the scattering vectors are the same, because it's all the same monomeric structure. It's just you've got these long interparticle interactions for the aggregates, and so it's showing up more at low resolution, but not at high resolution. So how does this affect a Gagné plot? So you can see that our perfect data down at the bottom here in red is nice and linear. And what happens is that as you increase percentages of these larger aggregates, you end up with slightly more curved Gagné plots each time. It's also reflected in the pair distribution function. For the 0%, we're fully monodispersed data, you get this nice reconstruct, or a nice P of R function that decays to 0 at 45 maybe. But as you increase even small amounts, small percentages of aggregation, you get these longer and longer tails. And so this is a telltale sign of aggregation, that you sort of get these extensions in your P of R function. And so you can see that just a small amount of impurity in your sample can have a big impact on the quality of your data. So there are also some effects of aggregation that you can test with things like Dmax and RG. You can see that Dmax increases quite substantially. Remember, I think at maximum here, we're only talking 7% of your sample is aggregated. Even at just 1% of your sample, you've increased by, you know, some 5 to 10%. So it's pretty significant. Your RG increases significantly. Your I0, which is directly a function of your average molecular weight, increases, as well as your Perot molecular weight. And so you can see that you're going to screw up your analysis if you don't have nice pure sample. In terms of bead modeling, this is sort of an idea of what happens to reconstructions when your sample is aggregated. You can see that for the nice monodispersed, no aggregates, we get a nice globular reconstruction of lysozyme. However, you notice that even with just 0.7% of sample impurity, we end up with this little sort of chicken leg extension kind of thing. And so if you see these types of reconstructions, when people run their SAXS reconstructions, they see these types of things. They're like, oh, it's a multi-domain protein and it's flexibly linked. This is fantastic. I'll get a paper. And it turns out, no, you're just looking for what's not there. And it's just a function of aggregation. So you want to make sure that your sample is really pure. Okay, so now I'm going to show some examples from some real data. And so in these cases, the structures from crystallography were known. And so this gives you an idea of how well the SAXS data can reconstruct ab initio envelopes and reproduce what it actually should. And so you can see that in general, for the most part, it got pretty good reconstructions in terms of, the shapes are reflective of the low resolution structures of the proteins. You can see that there's a few cases where there's some extra blobs, something like that, or that, or that. And so immediately you ask, well, is it aggregation, or is it actually some extra density there? Well, in the case of one here, it actually was extra density because where that terminus is, there's an extra 15% of the molecule or something like that. This case is aggregation because, for one, it's a dimer and it's not symmetric, which if it was really symmetric, it's probably symmetric in the case of a dimer. If it was really extra, residues that were not resolved in the density, you'd see it on both sides. And in this case, it actually is the real particle because there was about 20% of the molecule that was missing. So one of the ways you can test this is through these sort of like moles, or you can really. This is one of the reasons why SECSAX is becoming such a powerful tool, because it removes a lot of this ambiguity, because from your profile, your SEC profile, whether or not you're getting aggregation, for the most part. I mean, use your brain. So I'll just skip through some of these. You can see this was a nice case because they thought that the biological unit was a dimer. So you can see from the SAXS data that it's very clearly a monomer. Okay, so here's some NMR reconstructions. Okay, so NMR is a technique that you have these 2D or 3D spectra, and you're using them to use effectively some bioinformatics tools, knowing the sequence and assignments of the NMR data, and try and piece together all these short-range interactions to build up the tertiary structure of your proteins. And so what happens is you end up with some sort of low-energy reconstructions. And typically the way NMR data are displayed is that you show the, say, 20 lowest energy reconstructions. And you can see for NMR, a lot of times for these larger distances, it gets kind of crazy, and there's very little restraints for these long-range distances. And so this is where SAXS data can be particularly helpful. I mean, here I'm just showing, ab initio bead models that maybe it's not super helpful, but you can combine the NMR restraints with the SAXS data and really build some nice reconstructions that combine the high-resolution data of NMR and the low-resolution data from the SAXS. And so one of the questions is, well, why does it look like that? And which one is correct? Is the SAXS just wrong? Or is the NMR there's just not enough restraints? How does this work? Well, one of the things you could do is you could say, well, if the NMR were correct, let's simulate the SAXS data from that. And what kind of a reconstruction would we get? Because for one, the NMR is encompassing a very large volume, right? It's a very large volume, but it's an ensemble. So it's not like every one of these molecules has that large volume, right? And so with SAXS, it's going to reconstruct the shape. It's going to attempt to reconstruct the shape as best it can, but the problem is it's an ensemble, and so it's going to only really be able to reconstruct a single representative of this ensemble, because it has to be able to encompass the actual volume of the protein, right? And so if you were to take this particle and encompass all of that, the volume that you would see would be much, much, much larger than an ensemble average of each one of them combined. And so that's why your SAXS reconstruction just reflects effectively one average position. And I think this is just a nice illustration to sort of say, what do you expect to see from your ab initio reconstructions if you've got these kind of wildly dynamic systems? Okay, so you can also get some information about mixtures in using different techniques. And so here what I've done is I've actually fit, since we know the structures in these cases, I've actually fit the dimer and tetramer forms of these molecules to the SAXS profile and tried to figure out what the volume fraction of each one is. So you can see in the top case, turned out to be 63% dimer and 37% tetramer. But if you try and do an ab initio envelope, it actually comes up with something that's sort of a cross between the two. And so it's not fully reconstructing the tetramer envelope. However, when you get to something that's more like a 1-to-2, or a 1-to-1, where it's half dimer and half tetramer, you can see that the ab initio envelope looks very good for the tetramer. And that's because the scattering signal from the tetramer dominates the curve, because it scatters so much more than the dimer that when you actually do your ab initio envelope reconstruction, it tends to pull out the tetramer. Okay, so I tried to rush through that. That's effectively what last year's hour-long talk was. So now I'm going to try and go into some more advanced modeling. Do we have any questions before I get into this? Because that was a lot to take in. Take a break for a second. Yes?
Yes. So can you kind of separate out from that sort of one-dimensional curve, let's say, two different sets of ensembles?
So there are potentially some ways of doing this. Kushal will mention, I think it's Kushal mentions later, ensemble modeling. And there are ways of actually trying to cluster these ensembles to do exactly that.
So if you have 60-40, can you pull the 40 out?
Yeah, exactly. So it's tough because remember, if you're reconstructing multiple, effectively ensembles, multiple shapes, you're using those same 10 unique pieces of information to now reconstruct 2 or 3 shapes. And so it's that much worse of sort of an observation to parameter ratio. So your resolution and your fidelity in your models gets worse as you try and reconstruct more and more of the ensemble. Yeah.
Yeah, I was wondering how useful you thought it was for, or if there are specific techniques for modeling proteins you think are likely to be highly flexible, or
You mean
sort of
highly flexible in the
intrinsically
sense of-
disordered,
Sorry?
or intrinsically disordered, or have like large regions of flexibility.
Yeah, so ensemble modeling is sort of the go-to for this. People, if they have things that are, a lot of times you'll have fragments of structures known, and you'll know there's a flexible linker, so you could take the known fragments, and if you know it's flexible, you can do ensemble modeling, where I think I might actually, oh yeah, ensemble modeling. So maybe we'll get to that, and that'll answer your question. I forget half what's in this talk, but there's a lot of these fun things that we can do. This is an example of ensemble modeling, where it actually picks out different cases. So, yes.
Suppose you have a protein that's almost symmetrical and having 2 helices. And if you have an envelope for that, how we will determine which orientation is right for it? Did you get?
Rephrase that. I'm a little bit confused.
So you have suppose you have a protein that has like 2 helices and they are like almost identical but slightly different.
Well, it's going to depend on how slightly. Remember, it's a low resolution technique, so things that are slightly different at 20 angstrom resolution don't actually look different. So you just keep that in mind. I mean, if it's different enough at say 20 angstrom resolution, then I mean, typically when you're running these type, ab initio modeling, you're looking at a maximum of 20 angstrom resolution. Even if you collect your data to 2 angstrom resolution, you're still only able to reconstruct just because of the information content in the profile. So if you think about it in terms of the number of parameters you need to reconstruct an object at higher resolution, it grows as the cube of the resolution, right? So if you think of it in terms of reciprocal space, the volume goes up as the cube because we live in 3 dimensions, right? And so what happens is the SAXS profile, if you go out to higher resolution, only increases linearly. So your observation to parameters ratio gets worse by n squared at higher resolution. So you're getting that many fewer pieces of information relative to what you need. And so you have to have, even if you have higher resolution data, you still need to be able to reconstruct it. So your envelopes typically are 20 angstrom resolution max. I mean, it depends on the size of your structure rather than the size of your particle, but typically something like that. So if you wanted to be able to distinguish between helices, you'd have to have something that actually reconstructed to a resolution that was high enough to be able to distinguish between, which is unlikely. Okay, don't remember why the slide's in here, but it's getting better. So, use an Excel, I guess. Don't use an Excel. Whatever you do, you get. No, I shouldn't say that. I work for BioSAXS. Okay, so in terms of modeling, the fundamental way that modeling works is that you generate models, you calculate scattering profiles, and you see which of those models are the best, fit your data the best. And so the number one thing about modeling is that you have to be able to calculate your scattering profile very accurately. But you also want to be able to calculate it very quickly because you typically need to generate millions of different models. And so there's a lot of different algorithms that exist for this purpose. The basic sort of fundamental equation to use for calculating a scattering profile is the Debye equation. And so this effectively is a double sum, so it scales as n squared in terms of the number of atoms or the number of scatterers that you're using. And so there's this key piece where it's the distance between those scatterers. It's also modulated by what the scatterer itself scatters. So it's the form factor of a carbon atom or some kind of coarse grain bead or something like that. And so there's this sync function, sine of x over x. And it's a double sum over all the pairs of all the atom distances. And so it's a big equation. And so if you just do the Debye equation straight, it actually takes quite a while. But people have come up with some clever ways around this. Now, an additional thing that you need to think about is that when you're doing this modeling, you have to account for the solvent. Now, when you're doing the actual experiment, you subtract the solvent scattering, right? You do a buffer blank and you subtract it. But all that subtracts is the bulk solvents, just the bulk water, or salt or whatever it is that's in there, the bulk solvent. And what happens is around the edges of a protein or around the edges of a molecule in aqueous solution, water tends to associate slightly higher with slightly higher order, more often, effectively, than it does in the bulk. And so the average density of the region right around the protein, within the first 1 or 2 water shells, is 10% higher than it would be in the bulk solvent because effectively the water molecules are spending a little bit more time connected to associated with the protein surface. And so we call that a hydration shot. Now the other thing that we need to take into account is the excluded volume. So if you think about the fact that you're subtracting this bulk solvent, you have some volume of water that you've just shot X-rays through. And so through that volume of water, it's all water. But then what you do is you shoot this volume of water with proteins in it. And then the proteins are taking up some volume, which means when you subtract the water, you're not subtracting the bulk solvent around the molecules of protein. You're subtracting all of it, which means it's assuming that there was some water where the molecule was, where the protein was. And so that's what we call excluded volume. You have to account for the fact that your protein is excluding some of the water that was in the buffer blank that you shot. And so you have to account for these two terms. So the solvent contribution varies for different molecules. Obviously, more hydrophilic or hydrophobic surfaces will associate water differently. The chemical conditions can affect scattering terms such as contrast. If you've got a high salt or some component in there that scatters a lot, the relative contrast between the carbon and oxygen atoms in your protein are going to have a different overall net scattering than if you just had water, for example. So coarse grain methods help to speed up this process. They can sort of model a residue rather than an atom, and that helps to speed these things up, or beads or whatever it is you're doing. Most algorithms, the most common algorithms are an algorithm called Crystallography and BioSAXS. But there are a lot that exist, and these all give trade-offs for accuracy, speed, and complexity. So some of them have homogeneous, I think I've got a table here. So some of them have an implicit water layer where they just take your protein envelope and they expand it by 3 angstroms and they fill that with a uniform density and assume that's your water. But that's only accurate out to, 15 angstrom resolution, something like that. And so if you want to use wide angle scattering, you need more complex, heterogeneous solvation things, solvation approximations, and so some of them become explicit. They use molecular dynamics. It can get quite complicated. But you also need to trade this off with the fact that you want to calculate millions of different reconstructions to be able to do some modeling. So you want to balance this with speed. So there's a lot of different versions of these things. And this is outdated. And says 2012. There's a lot more now. You can see that for the most part, they actually all agree. They're particularly, they get to deviate more when you get to higher wide angle scattering. I don't even know that I would call this wide angle scattering. Usually above a Q of maybe 1, people consider wide angle scattering, maybe above 0.5. So that's for calculating the scattering profiles from the model. So how can we actually utilize this? All right, well, let's start with one of the things that people do most often. You have a structure, ab initio models are great. In all practicality, they're not particularly useful. They're good for comparing against things. But if you want to actually get some, functional information, a lot of times people will have other information. SAXS is most powerful as a complementary technique, not as a standalone technique. And so one of the first things people do is rigid body modeling. Well, maybe the structures of a few components or a few fragments, and you can get the scattering profile in solution, but maybe you can't solve the structure of the complex because there's a whole host of new crystallization conditions and concerns when you're actually dealing with complexes in crystallization. And so maybe you can get the structure of each independently. And so what we do is we take these, say in this case we found the structure of this and the structure of this. We take this structure and this structure and we search 6-dimensional configuration space in some intelligent ways to like simulated annealing to try and find what arrangement, what translation of B relative to A and rotation of B relative to A is going to give us a scattering profile that matches our data. And so we model this. And so you're minimizing chi-squared, and again, a lot of times you're using some of these real space restraints, like don't leave it this far apart because that's not useful.
So, in terms of chi-square, so what's an acceptable number?
Yeah, so nobody should ever use chi-squared ever. The reason I say that is because it's rare that when you collect your data, your errors are accurately calculated. There are some tools now that can help you to sort of translate to better errors. And if your beamline scientists are really, really, really pedantic, they might be able to get you accurate errors. Chi-squared is fundamentally based on the errors that are in your data profile being correct. So these cases, they're really just minimizing chi-squared. You can have something, for example, if you have noisy data, like if this data were to be really noisy, right? I could have a scattering profile that's up here or down here, and it would give me a chi-squared that maybe is very similar to what this is, even though it wasn't as correct. And that's simply because if the errors are larger, you're allowed to have more incorrect models. And so ideally a chi-square should be 1, in the perfect world. But it also depends on how noisy your data is, how high of a resolution does it go, and how well your errors calculated. So, you could have perfectly legitimate models that have chi-squareds of 3 or 9. Yeah, sure, because it just depends on how your errors are calculated. Yeah, I mean, plus a lot of times you'll get like, you'll get like a bump out here, and all of a sudden everything's off by an order of magnitude for that bump, and it screws up everything. There's better ways than just chi-squared, more statistically robust ways, but that's kind of more advanced now. There's lots of papers on, actually I don't know if there's lots of papers, but there are papers on accurate calculations. It's important to always do, this is one of the reasons why ab initio envelopes actually are useful. Ab initio envelopes give you an unbiased look at the envelope, and so your rigid body model should fit your ab initio envelope because that tells you that it's just coming from the scattering data. Okay, so one of the programs that's most common for doing rigid body modeling is called SASREF. This is part of the ATSAS package. There are others, but this is just one I picked. And so you can search for multiple subunits, domains, or put complexes together. Other programs such as Coral, I don't know if Bunch is really a thing anymore, but Coral can do things like where you have multiple components, you can add in symmetry, you can say this is a complex, you can do mixtures of things. It's actually quite advanced. You can also say, okay, maybe I've got some, I don't know, maybe I got some PRET information or some kind of EPR data or something like that that says, I know that this residue over here is actually within 10 angstroms of this residue over here from this experiment. So you can add in these contact distances to make sure it keeps those residues close to each other. And this is a great way of combining all of these things. You can actually also do multiple scattering profiles. So you can fit these simultaneously. So if you've got, you know, A and B, and then you've got B and C, you can try and fit them together. Now the fundamental assumption of that is that the structure of A and B looks like A and B in A, B, and C. And so that's the fundamental assumption you're making, that there's not some conformational change upon binding of the C component. And so that's an important thing to keep in mind because that's not always the case. Okay, so some more recent advances. What time do I have? When did I start? 10 minutes?
Have another, say, 15.
15 minutes, okay. Is that you can do rigid body modeling with mixtures now, which is really great because a lot of samples are not really amenable to this idea of monodispersity. You know, a lot of samples just be like, I don't want to be monodispersed. I like half the time hanging out with my partner over here. And so there's these transient complexes that you just can't get rid of no matter what you do. And so we can actually now account for some of these, low-level mixtures. Now, like I said a little bit ago, when you're doing this, you have to keep in mind that you only have one scattering profile, say one scattering profile, and so you've only got 10 pieces of information. But now you're trying to reconstruct 2 complexes or 2 molecules, and so it's twice as hard of a problem with the same amount of information, and so you have to be a little bit more suspicious of what it comes up with. But it is possible, and one of the advantages is that a lot of times you can't fit a single scattering profile with a single model, because if there's a mixture in there, it's not going to be able to reflect that. And so, for example, this mixture version of SASREF allows you to actually take the sort of main rigid body reconstruction that it's doing and break it down into its subsequent pieces and do this sort of oligomeric volume fraction fit to your data to try and, you know, fit as best it can to the experimental data. And so this can actually help you calculate volume fractions as well. Okay. So rigid body modeling is great, but we can do a little bit better if we take into account the fact that these structures are high resolution and there's some information about energies based on the atomic locations and the energy surfaces of these proteins, of these molecules. And so we can combine the high resolution information that docking provides us, if you've ever done docking before, with the low resolution information provided by SAXS to get more accurate complexes. So the way this works is that, say you have, 2 independent, A and B. What you do is you effectively roll B around the surface of A, and you calculate just how docking works in general, and you calculate what the energies are. You calculate how well those 2 molecules interface. What's this, the surface area of the boundary? What are the electronic and energetic interactions between them? And so it maps out an energy surface to say these are good locations, these are bad locations. Let's isolate them and cluster them. And so when you cluster them, you can say, okay, it's most likely here, it's most likely here, but there's a lot of possibilities, right? But what happens is that these possibilities could be distinguished with SAXS. Because at low resolution, they're going to have longer vectors that you can distinguish by. So this is how we do it. So we do the same thing. We determine our candidate conformations. This is just one approach, but there's a few different ones. This is sort of the basic idea. You coarsely filter those models based on the gross size characteristics, like RG. So if you've got, some molecule that looks like this and some molecule over here, your RG will be different than if the molecule was inside of, this molecule A. And so that allows you to sort of filter out without having to go through the whole calculation of the scattering profiles based on thousands of candidate conformations. And then what you do is your remaining conformations, you calculate the full SAXS profiles for each, and then you cluster them and come up with the best possible candidates, and then you can do some conformation refinement. And this allows you to combine the advantages of SAXS, which are low resolution information, with the advantages of docking. And so SAXS helps you to minimize the number of candidate assemblies, which that's the big issue with docking. You can just run docking without SAXS data, but you get lots of conformations, lots of different candidates, and it's really difficult to score those appropriately. And so SAXS can help you weight those scores with some experimental information. Okay. All right, so hybrid modeling is where you're going to take a lot of these methods and throw them all into one big bag. And you're going to take all of the different methods that you can, take all of the different pieces of information from all the different experiments you did, and throw it into one massive, multifaceted modeling approach. That includes some NMR data that I mentioned, but you can do SAXS, you can do neutron scattering, you can do wide-angle scattering, NMR, residual dipolar couplings, which is a type of NMR, X-ray structures, and throw all of this stuff. You can actually throw in other things too, but FRET, distance restraints, things like that. And so there's some of these hybrid modeling platforms like Explore-MH and IMP that allow you to throw all this information together. So this was one really nice example of this from, it's actually kind of outdated now, but it was one of the first implementations of this, or first examples of these implementations. And so this combined analytical ultracentrifugation, isothermal titration calorimetry, structures from X-ray crystallography, NMR spectra, RDCs, SAXS, WAX, SANS, and this hybrid modeling. It threw everything together in this really kind of tour de force. And I'm not going to go into everything because you can just read the paper. Have fun. It's a long paper because they did so much, but it's a really nice paper, I think. And it's really a large complex, which is typically too large for NMR. They use NMR as one of their core pieces, but it's a large complex. I'm not showing the full complex here, but here you go. It's the full complex. It's a large 150 kilodalton complex. You can't do that with NMR typically. However, they were able to piece out a lot of this information by combining SAXS and WAX data with these. They did some flexible modeling, ensemble modeling of things. They used SANS data for validation with contrast matching, and came up with a whole scheme for the different mechanisms of how this complex formation, conformational changes, and reintegration. Okay, and then finally, I'm going to talk about some really neat stuff that's going on in time-resolved SAXS. So a lot of people are interested in dynamic catalytic reactions. And so, for example, things that change as a function of time. You want to see folding or unfolding of a molecule, or you want to bind a ligand and find out what conformational change takes place. But you want to see how it happens, because it's not always the case that from point A to point B that you can get enough information. So you want to actually see how it gets from point A to point B. And that's where time-resolved SAXS comes in. So there's two main approaches to time-resolved SAXS at the time, currently. There's mixing and there's pump probe. So mixing is where you take one solution, say protein, and you have another solution that, say, has ligand in it or something like that, and you flow them together. And, for example, in this case, we're using RNA, and RNA folds when it's in a buffer of magnesium. And so they're actually watching the folding process. So you have your unfolded RNA, bring in either through, a lot of times it's microfluidics nowadays to have fine control, but you can do it with just flow cell geometries. And you flow these together, and then as a function of time, they're diffusing, the molecules of magnesium are diffusing into the, sort of the jet of RNA, the stream of RNA, and causing it to fold over time. And so you look at a different point with different probes, and so as you go from point A to point B, you assess scattering profiles as a function of time. You're sort of translating space into time. And so you can see that you can watch it fold over time. Now this is to the point now where you can have sort of sub-millisecond time resolution, and this is actually getting even better now, in that I think I actually get more, I'm getting more detail as I go. I forgot I had other slides. So there's two types to this, stop flow and continuous flow. And stop flow is when you have two separate syringes, and you pump them together, and then you let them sit and diffuse and interact, and then you wait some period of time before you image it. But they're sitting in the same mixing region. And so this typically has a limit of something like 10 millisecond time resolution. The advantage is that it doesn't require much sample because they're just sitting in the vial together. And then there's continuous flow, which is this example that I just mentioned, where you actually have this sort of jet and it's continuously flowing and you're translating distance to time. And this can have up to sub-millisecond time resolutions. And actually now you can even get into just a few microseconds, which microsecond time resolution is amazing because most biological processes happen slower than microsecond. Now lots of them happen in the nanosecond, but a lot of that below that point is sort of more chemical reactions. So for a lot of, particularly for SAXS, which concerns more large conformational changes, you're looking at milliseconds is perfectly suitable, or sub-milliseconds perfectly suitable. The disadvantage of this is that it requires large sample values because you're continuously flowing this. Okay, so there's some new mixing jets that allow you to mix different things together. And this is what I was talking about, has very short time resolution of sub 250 microseconds. This was that example of RNA folding. You can see that as a function of time, the radius of gyration decreased in the sort of biphasic mode. And this is a Kratky plot that we talked about earlier. And you can see that as a function of time, we start with an unfolded Kratky plot. You notice that it rises and then plateaus. But at the end, it's getting more and more folded. You're getting more of this bell curve. And so that as a function of time is showing you the folding process of RNA. Okay, so then there's pump probe. Now pump probe has some advantages and disadvantages. The main advantage is that it's extraordinarily fast. You can get picosecond and sub-picosecond resolutions pump probe, provided you have the right light sources. So there's Synchrotron or XFEL. You use these liquid jets that I just showed. And the time delay is set by the delay between the pump. Say if you have an infrared or visible light, say you've got, photo system, something like that, that's light sensitive. You pump it with your light that, makes it green or does whatever it does. Then you wait some time. So the time delay is just really a coordination between the pump laser and the probe laser. And so you can get these into very short time frames. And so synchrotrons are going to be fundamentally limited by the length of the pulses. So in the case of synchrotrons, it's like 100 picosecond typically. There's something like 10 to the 8 photons per pulse. Notice that's per pulse. That's not the flux of the synchrotron, but it's the photons within a single pulse. And typically you're looking at greater than nanosecond time resolution. Whereas with an XFEL, you have extraordinarily short pulses. We're talking femtoseconds. And you have very bright pulses, 10 to the 12 photons per pulse, and you can get sub-picosecond time resolution. So here was one of the was really the first example from an XFEL, and you can see the scattering profile. This is actually wax, not SAXS, but just as a demonstration. You're seeing the scattering profile change as a function of these extraordinarily short periods of time. And they're able to combine all of these scattering profiles and extract information from the sort of the ensemble of scattering profiles using a form of singular value decomposition, which extracts sort of these dominant vectors. And you can get what's occurring in solution as a function of time. And they notice things like a protein quake. The protein is actually quaking with energy as it absorbs light, amongst other things. And I think this is just a little video of that sort of flexing that they were able to do some modeling to fit that. And I think that's it. Yeah, so. Are there any questions? That was a lot to get through, and now I'm sure you're ready to explore.
That's one that you passed very quickly. It's called
Yes.
time resolve wax. What is that?
That's this. This is time resolve wax.
Oh, it's the same thing.
Yep, it's the same thing. I just skipped that because it was an explanation of what the...
Well, yeah. So, this is one of my related to it.
Yep, yeah, it's the same thing. I just skipped it because I figured I was going into it in the next slide. Yes.
I meant to ask this earlier. How are you able to distinguish between like these abnormal globular extra densities and just a protein, like a region of the protein sample confirmation to solution?
Yeah, so that's where
Like
these sort
like
of,
two helices just branching to a close hidden open state.
yeah, that's where these, you really do need some, like you could study concentration dependence. A lot of times aggregation is a function of concentration. And so that's one way to assess that. It's not always the case, so really what you need is sort of mols or SEC-SAXS or something like that to have a sort of an ancillary piece of information to confirm that you're looking at what it is that you can do.
Thank you.
The answer is almost always complementary biophysics.
Yeah. Yes. Oh, actually, before I answer that, one thing that you can do is the molecular weight will change as a function of aggregation, right? You'll see shifts in molecular weight, but if it's conformations, you should get the correct one.
Okay.
Yes.
Is there a term like occupancy in ab initio modeling to take into account the conformational variation?
So this is where ensemble modeling comes in. So ensemble modeling is effectively that. There isn't an ensemble version of bead modeling, but the ensemble modeling a lot of times can have any sequence to it. So you can do sort of unfold it, and so in that sense it can be ab initio without the need for structures. But it gets rough in terms of how accurate that is, because there's a lot of constraints. But not in terms of just like bead modeling. There's no ensemble version of bead modeling.
And how computationally expensive these modelings are? Is there any benchmarking?
I mean, your average bead model will take, if you run it in fast mode, a minute. If you run it in slow mode, an hour. And you're going to run 10 of them and average it, and the averaging process is usually the longest. So, you know, I mean, if you want to do something publication quality, expect, what, 5 to 8 hours, something like that. All right. Okay.
Okay, since Richard is working to be one, I'm actually going to give his presentation on data publication. So, my name is Jesse. I was a postdoc at MacCHESS for about 2 years. I'm now a beamline scientist at BioCat, which is a solution scattering beamline at the APS, where we do very similar types of things. So, this lecture is intended to be just a very quick overview of the things you should do when preparing a paper with SAXS data. And so I actually added in a couple slides this morning to update this, but people have put a lot of thought into this, and the key point is really this publication here, 2017 publication guidelines for structural modeling of small angle scattering data from biomolecules in solution. Exactly what it sounds like. A bunch of people sat down, very carefully went through all the different pieces that you need to put together, how to accurately represent your data, make sure you have all the information you need to evaluate it after the fact, if someone's reading your paper, make sure that you did good quality scattering. So the key points in this paper, I think it's worth reading all of it, but they have 4 tables that list all of the details that they recommend reporting for sample prep, data acquisition and reduction, data presentation, analysis, and validation, and the modeling work. And so taking a look at those 4 tables is very key. It includes a comprehensive workup of a SAXS data set where they kind of go through all the different bits and pieces. And then they have this supporting information that contains a really useful table where they collect all the details that's available as a Word document, so you just download it, fill it out with your system information. This is just a very quick look at like the first part of it where they have, you know, all the samples, where they come from, all the different bits and pieces they recommend that you have in there. And so I added those 2 slides this morning to say that there's a new version of this. This is the original version of that paper. You can see it's the same thing without the 2017 and the colon and update on it. And it contains a lot of very similar information. So the really key points here is that, as we've been talking about, SAXS is a very sensitive technique. A lot of things can go wrong. You can get bad data in a lot of different ways. And so for people to accurately assess whether or not you've done good work, you need to give them a lot of information, right? You can't just, as with crystallography, give them the crystallization conditions and they know if you've got crystals that work, right? There's so many things that can go wrong with SAXS. So you need to really include evidence of sample purity. Kushal talks about figure 1, where you have to prove to the reviewers and to yourself and to anybody who's reading the paper that you know what is in that solution and that you know exactly what you are scattering from, and you can show that it's your organism of interest. You need to report exactly what your buffer was and how you got your matched buffer, because again, that's something that can really mess you up. You need to report sample concentrations and how it was measured, because that's going to affect all the downstream analysis of molecular weight and things like that. These days, it's actually recommended that you report not just, say, UV measurements on a nanodrop, but also the extinction coefficients you used and how those were obtained, whether it's theoretical or actually measured. Even if you don't have space for them in the main paper, you're just showing interpretation of the data, you should always provide the scattering profiles in the sup, if nothing else, so that people can look at it, see if you had any aggregation, things like that. The raw profiles are very informative for looking for details of what can go wrong. So those always need to be somewhere in your paper presentation. You have a method section, so you need to include exposure times, wavelength, that kind of stuff. We have a sample method section a little further, so I'll come back to that. Richard emphasized this point, but you can't get rid of data just because it doesn't look good, right? You have a couple weird, scraggly key points at the beginning of your profile. Those need to be in there, right? Those, as long as your beamline scientist is telling you that's real data, then it needs to go in the paper. You can't just throw it away and pretend that everything was absolutely perfect. So honest about your data presentation, honest about what kind of sample quality you have. We'll see an example actually in the tutorials tomorrow, where even if you cut off the first few points of an aggregated sample and you get a beautiful looking Guinea, it still actually gives you a different RG and a different molecular weight, and it kind of affects all the downstream propagation. And so knowing that there was aggregation in that sample is very key to understanding what went wrong if someone's trying to replicate the experiment, for example, or even if you're trying to figure it out. Other things to do, so we've talked about 2 different ways of obtaining the radius of gyration, one from the Guinea fit and one from the P of R function. You should present both and compare both, and ideally they should be the same. Same goes for I0. When you're showing scattering profiles on a plot, because you have this Q to the -4 decay, typically, there's a huge range of intensity that you cover in a standard experiment. So it's typical to put them on either a log-lin or a log-log plot. And if you don't, it can easily hide details that would otherwise be obvious and relevant for your experiment. So plot I of Q on a log scale. For envelopes, this has changed a little bit since Richard put the slide together. We actually talk about this in the tutorial tomorrow, so take a look then. Does the P of R look good? Tom went into various ways that this can go wrong, various things that can go wrong with that. But make sure you're showing the P of R function somewhere so people can assess whether or not you did a good job with that. Again, that can go in the sup, but that's the kind of thing that needs to go in there. And then if you're reporting a P of R function, that's analysis you do need to report kind of the back transformation against the data so people can see how good a fit you got against the data and whether or not, again, it's another way of assessing the quality of this P of R function. So it's really all about presenting enough information that there's so many little ambiguities, so many things that can go wrong. You want your readers to be sure that you did a good job at the data analysis and you actually got a result that's meaningful. So, you have to convince both yourself and you have to convince everybody else. So things to watch out for. So if you can, report errors on all of the numbers you report. This it sounds like it should be obvious, right? But it's not always straightforward. Often estimating the uncertainty in your results can be quite tricky. It depends on how noisy your data is and things like that. But for RG, for example, there's now raw now includes an automated way of estimating this, but we'll talk about that again in the tutorial. There's some tricks to kind of really nailing down where your uncertainty is coming from. The problem with RG is you have uncertainty in the fit for any given range that you picked, but there's also uncertainty in how you picked the range. So there's kind of two sources that can contribute to this, and it can get a little bit complicated to figure out which one is dominating your system. For RG, you should always be, again, reporting these ranges that you fit over, because that's very important. If you fit it too far, or you have a very small range of Q that you're fitting, it's likely not giving you good results. As Richard mentioned, for standard experiments, you need to do at least 3 concentrations if you're running in batch mode or robotic mode, as we call it here. Otherwise, that you may have concentration effects that are hiding. For SEXX, you don't need to do this because you're sampling over the entire elution peak, so you're already sampling a range of concentrations. So that's built into that experiment. And Steve will talk about that momentarily. But you need to have, for a standard experiment, multiple different concentrations so you can make sure that it's not changing its concentration. And that's very critical. The other thing to do, and we do this by default, is you need to have several exposures, right? If you just have one exposure, one long exposure for 10 seconds instead of 10 1-second exposures, there may be radiation damage hiding in that one exposure. You want to take multiple exposures and make sure one after another is all the same. And then we've talked about kind of estimating uncertainty and molecular weight. Make sure you're accurately understanding the limits of that analysis in SAXS. So there's more. The total estimate. So when you do genome, it reports back various statistics. So you should be reporting those, and you should be ideally only using good statistics. And we'll go through what those are in the tutorial tomorrow. So I'm not going to talk about this section too much. But determining a good PFR function is, I hate to say it, but it's almost more of an art than a science. There's a lot of little interpretation calls you have to make, and so it's really a challenging piece to make sure you get absolutely correct. And as Tom said, that often leads to large uncertainties in Dmax, 5–10% more. Ambimeter was already mentioned briefly, but determining whether or not your 3-dimensional reconstruction is any good is worth doing even before you do a 3-dimensional reconstruction. Talk about that in the tutorial tomorrow. Talk about that in the tutorial tomorrow. Talk about that in the tutorial tomorrow. This is a key point, though. Use multiple methods to confirm your hypotheses, right? And what I want to add to this is that SAXS is really best when you're model testing. So you build a model and you test it against the data set. Building envelopes is fun. It makes lovely pictures for your PI or your presentation, but it's usually not as useful as doing a rigid body modeling and testing it against the data or whatever it is you're interested in. That tends to be a much more accurate way of determining whether or not something is real. And I think Kushal had a quote in his slides that I'll paraphrase, that something to the effect of SAXS is much better at determining what something isn't than what something is. So it's a very good way to eliminate possibilities, but it can't always tell you for certain what it actually is once you've gotten rid of those possibilities. So this is more for your reference. I'm not going to read this, but this is what a standard method section from our beamline might look like. And so this, as you're kind of writing up the data, gives you a starting place in terms of the information you should include about the beamline and the exposures to really be able to accurately describe the experiment that you did here. And so this is included for your reference for hopefully when you go home and write up all the beautiful data you collect tonight or tomorrow or the day after. And there's some good things to take a look at. So I think all of these have maybe come up already, but we provide a list of good review articles to get an understanding of some of the fundamentals that we've already talked about here. Classic text as well. I think most people have read most people who are very serious about scattering have read at least some of the glider and Kratky texts. It's certainly one of the classics in the field. It's a little dated these days, but it's worth taking a look at. Other resources for getting help. So, you can read the articles. The AdSAS guys also run a forum where you can ask questions either about data processing with their software or more generally about data processing. It tends to get better answers when you're asking about their software, as you might expect. But they do have some, there are other people who read the forums, so we can sometimes get other answers. And then the last thing that Richard has in this presentation is please cite our facility, right? You're coming here, you're using it. So it's not only important to acknowledge MacCHESS in the acknowledgements with the grant number, which is in that red folder, I believe, in your binder, but also cite the papers that we've written about the facility. This is how we can prove to people that people are actually using our facility. It's how we can get funding. It's how we can continue to exist, and in that way, continue to serve you and get you guys data. So it's very important to make sure you do these kinds of things, both for our sake and for your sake in the future. So the most recent Beamline paper is the Cicervo paper. It's Richard's actually old postdoc, Alvin. This is a protocol paper that you may find useful that I believe someone earlier today showed, maybe Kushal, had a list that included this protocol paper on actually how to carry out standard synchrotron experiments with small angle X-ray scattering. And then this is actually, if you open up RAW, it'll pop up a screen with this citation. It's not in your slide, I believe. But this is the most recent paper we've published on the data analysis software. So as you're going through this, as you're writing up the papers, make sure you acknowledge the facility appropriately so that the facility can continue to exist and continue to give everybody what they need. I'm happy to take questions. I know that's a very brief overview of publication. I mostly wanted to point you at the resources, the two papers that are particularly relevant. And of course, those of us here or your Beamline scientists, wherever you're working, are happy to answer questions and kind of review method sections and make sure you're including the right kind of supporting information to make sure all the details are there as you publish this type of work. So I'll take questions if you have them, and if not, it's just about time to hand it over to Steve. Yes.
I was just going to ask, do you know if the recent paper about the new guidelines, does that include resolution for bead? Because I didn't really talk about that. Maybe I should add it.
It's been a little while since I really thoroughly went through that paper, so I'm not sure. I think they recommend including it in the resolution estimates, but it's not a. I'm not sure anyone really agreed on exactly how that should work. So. Other questions? This is mostly for future reference. All right, thank you, Steve. So, switch to other hats now. Steve Musburger is a postdoc in Endo's lab at Princeton. He's an expert SAXS user. He's been using the facilities here at CHESS for, 10 years now, something like that.
Yeah,
that's right. He's actually the one who first taught me how to set up a Beamline at G1 many years ago. We were both graduate students, and he's going to talk to you about SEXSAX, which is no longer an exciting new technique, but now a very exciting established technique for getting excellent data quality out of your samples. And I believe you talked about some advanced processing techniques for SEXSAX as well.
yes.
Take it away.
So, Jesse, are you watching the online questions?
Yeah, we'll do that.
Okay. So, hello, especially for those of you online. If you have questions, if anyone has questions during the talk, please interrupt me. Same goes for the online people. I think text, post a comment, and then Jesse will raise his hand. So this talk will be kind of broadly about chromatography coupled SAXS, and I'm also going to bring in an example sort of from my own research that sort of brings together a lot of different techniques to study protein allostery. So you'll get an idea of how different ways of collecting SAXS data can work together to support a model for a story. So as Jesse said, SEC SAXS is becoming very popular. This is just the number of publications per year that mention SEC SAXS when I do a Google Scholar search. So, for a while it was kind of simmering on the back burner, and then around 2016 it's really started to take off. And this is, for 2018, we're only, a few months in, we're already getting pretty close to 70 publications, right? So this is becoming a really important technique. In this presentation, so the first part, I'm actually just going to go through what size exclusion chromatography is. The reason, most of you are probably using it in your protein purification, so you sort of know how to do it already, but I'm a little sensitive because I was a physics student, and when people talked about SEC, I had no idea what they're talking about. So for those of you who are physics students, this is for you. Okay, and then part 2 is really how to collect and interpret SEC SAXS data. And in part 3, as I said, I'll go into this case study, which is really about protein allostery and regulation. Okay, so the size exclusion column, basically you have a bed which is composed of beads, and you flow across the beads, and the beads are porous. So you have, in blue here, this is showing the running buffer, and white are the beads. Each bead is usually composed of some porous material, in this case, like a cross-linked agarose with dextran. And the idea is that you create pores of pretty well-defined size so that certain sized molecules can go inside and certain sized larger ones are excluded. And it turns out that when you flow across these beads, if you start out with a mixture, in this case you have a mixture of yellow, orange, and red, which show up as brown at t=0, they'll separate into different bands. And the red, the large object, comes out first because it has less volume to explore on the way, whereas the small object comes out last because it's going in and out of these pores in the bead. The typical way you would set something like this up is, for example, using a fast performance liquid chromatography machine. This is basically a way of automating this whole process. So you have pumps, you have an injection valve, which allows you to store your sample temporarily in this loop of tubing, so that when you're ready to inject it on the column, it can just push through the tubing onto the column. Typically, you would flow through a column and then into a series of detectors. So the standard ones would be like a UV vis detector for measuring concentration, conductivity sensor, which is perhaps less useful, but it tells in this case, but it tells you basically how much salt you have. You can measure pH, and then you would typically collect the fractions, for example, for further purification or analysis. Now, when you're looking at a chromatogram, it's good to know sort of the terminology of what these different things are. So at the beginning, this is when your largest stuff, so horizontal axis here is usually volume or time. So the first thing to come out is on the left-hand side, and this is typically the largest object. So this V0, this is the volume that would correspond to the void volume, so excluding the beads. So this is the volume that the largest objects would explore. And then on the far right-hand side, this is the total volume of the column. So this is the volume that the smallest objects would explore. And so your proteins, as they come through, will partition somewhere between the void volume and the total volume. And you can assign a partition coefficient between 0 and 1 to each of these peaks. So again, your low molecular weight stuff's on the right, your high molecular weight stuff's on the left. There. And for globular proteins, this is an example of, I think, a commercially available calibration set of proteins. So for a typical set of globular proteins, they tend to fall on this straight line when you plot log of molecular weight versus partition coefficient. And so this is how people typically calibrate their column. And yet you end up with this linear relationship. So the volume where it comes out is a function of the log of the molecular weight. Okay, so there's a big caveat though. SEC also depends on shape of the molecule. And people that do RNA are really aware of this because RNA tends to be highly elongated. And so it will actually partition as if it were about 6 times higher molecular weight than you expect. So, so the axes are reversed on this plot from the previous one. So molecular weight's on the y-axis, solution's on the right. So that's a 6-fold difference. So yeah, when you're choosing your columns, just be aware that molecular weight cutoffs might only apply to globular proteins and not to your RNA or highly elongated protein. SEC columns come in a wide range of sizes. On the left, this is a typical prep grade column that you might use in purification. There's also smaller analytical scale columns and also very small sort of convenient columns. This is, for example, a centrifugal desalting column that I'll talk about in a minute. So these prep grade columns are often used as a final purification step. I think most protein labs I've been to have one of these or many of these. And great thing is that the running buffer that you use in your final step of purification is often a very good buffer match for SAXS. So hang on to that. You can check sample purity from the profile shapes, or you can also run them on SDS page. So it's a good thing to do. These analytical scale columns are also really useful. You can check oligomeric state impurity. You can check, for example, whether you can screen a wide range of buffer conditions and see if certain conditions will favor dimers or reduce the amount of aggregates, for example. And these are often combined with light scattering, secmols like Vishal discussed. Ando Lab really likes these quick spin columns. We usually bring a bunch of them to the beamline because you can rescue bad buffer matches. So basically, you load your sample on the top and flow through, and their typical volume is 75 microliters, which is about what you would normally use for a few SAXS data points, maybe. So it's a convenient size and has 99% retention of salts. Anything larger than 6 kilodalton will pass through. And these are actually more gentle than spin concentrators because you're not increasing the concentration and diluting repeatedly. So they're a little more gentle if your protein is prone to aggregation, which I guess most are. Okay. So before I move on to the second point, I'd like to pause and see if anyone has questions about SEC. Okay. So collecting and interpreting SEC SAXS data. The typical setup is really simple. So basically, I've shown you this part. This is the FPLC. Basically, all you do is pipe the output to the SAXS beamline. And so you, as things elute off your column, they just flow continuously through the X-ray beam, and you just collect data. This is what it actually looks like at G-line. This is maybe a year out of date, since this is an older FPLC, but essentially you have the FPLC sitting in a refrigerator, and this is the sample. Right here is the sample cell in the SAXS beamline, and X-rays are coming in from the right, and this is the output of the FPLC, and it's just been piped directly into the flow cell. I can point out a few other features here. This syringe is the injection port for your sample. Up on top, these are the buffer reservoirs. And what you can't see is the UV and conductivity cells. And then there's an array of columns available on this particular instrument that are right here. Okay. So So the basic workflow, as I said, is you flow continuously, you collect a whole big stack of scattering images, and then you integrate them, and what you end up with is a data set that I like to visualize in 3 dimensions, right? So you have intensity, scattering intensity on one axis, you have Q on the other axis, and then you have frame number. So if you sort of slice it along this direction, it looks like a chromatogram. If you slice along this direction, it looks like a scattering profile. And because you have all this data, you can subject it to sort of powerful deconvolution methods. And I'll talk about this a little bit later, and we'll also mention them in the workshop tomorrow. Okay. So this is just a quick example I thought was kind of fun. So, you know, Kufal said you must know exactly what you have, and you must purify it and characterize it. This is an example where I just did something stupid, which is I took BSA powder and I injected it, dissolved it in water, and injected it, and just saw if I could get a reasonable looking bead model. And the answer is that you can. Okay, so this is what that looks like. So yeah, I dissolved it in some Peaks buffer. I used the SuperDex column. I pre-equilibrated the system, and then I injected the BSA. So actually, the BSA was not even in a matching buffer. You'll notice that I didn't have glycerol in the buffer. It didn't have NaCl. So that I was relying on the SEC to give me a good buffer match. So I injected in the sample loop, and I collected 1,000 images. This was done at CHESS a couple years ago. So when you look at the chromatogram, what you see is this kind of a shoulder here, and blue is the UV, and then you have a main peak. And in the conductivity, you see this dip. This dip is occurring at the total volume of the column, and that's because there was a hole, basically, where there's no salt, right? Because the solution I injected had no NaCl. So it's nice. This is, you know, this is sort of proving to you that I got a good buffer match because that hole of no salt came out altogether. So this is monomer. You know, one question is, what is all this stuff? It's probably dimers and trimers. And this is the salt deletion peak, or salt depletion peak. Now, if you just plot all of these 1,000 SAXS profiles, it looks like kind of a mess. So, you know, you have most of this is just background scattering, and then when the peak comes out, you get just a little bit of protein scattering. So what do you do with this? Well, one thing you can do is you can plot the total SAXS intensity. So this is if you just take all of the intensity values and you add them up for every value of Q, you can make a sort of chromatography type peak, and that's what this is. Raw will calculate this on the fly as your data is coming in too. So it's a useful. You can compare it with UV, for example. And you can see many of these features in the total scattering peak. You actually see the dip where that lack of salt came through, and you see the main peak and also the shoulder.
Question.
Yes.
How long you did the testing? So the flow was coming out and you were shooting, and every time was, how long was it?
So each image in this case was 2 seconds long, and I was flowing at 0.1 mils per minute. So the second thing you can do is a Guinée analysis across the peak. So what you do is you take every time point and you do a Guinée analysis, and it's done automatically. You don't have to do it by hand. And then you can look at RG through the peak. And what you want to see, ideally, is that RG is constant. That tells you that the peak is likely a single conformation or a single oligomeric state. And you see that in this shoulder, before the main peak, RG is actually quite a bit larger. Okay. So at this point, I'm going to introduce singular value decomposition. Has anyone heard of singular value decomposition? Okay, we got a couple. Has anyone used singular value decomposition? Okay, good. Anyway, it's so you don't. Well, yeah. So singular value decomposition. It's a linear algebra method where basically the goal is you want to take your data set, which we'll call a matrix A. So in this matrix A, each of the SAXS profiles is a column in the matrix. You want to represent it as a product of three matrices. This matrix U, you can think of as, this is called the left singular vectors. You can think of this as a set of SAXS profiles. The matrix V, these are the right singular vectors. These are a set of dilution profiles. And then S, this matrix, is a diagonal matrix of weights that tells you how you need to multiply the dilution profiles by the SAXS profiles in order to reconstruct your original data set. And the great thing about SVD is you can pull out kind of a minimal set that you need to reconstruct the data set. So in this case, I'm doing SVD on that BSA SEC data set that I just showed, and there are only 3 singular values that are significant. And that means if the rest of these are just involved in reconstructing the random noise in the data. So you can just throw these away and get a smooth version of the data, for example. Another way that this is useful is, well, okay, so I'm looking at this peak, and I want to select a part of the peak to average. How do I do that, right? So if we do the SVD of the whole peak, we get 3 singular values. So we obviously don't want to average all these curves together because there's 3 sort of separate components in there. So if you cut off this end part, this is remember the salt depletion peak, that actually reduces the number of significant singular values to 2. And furthermore, if you cut off this peak at the beginning, now we just have 1. So that tells us that basically all of the data in this blue region are just basically rescaled versions of the same curve, effectively, and average them together. And the average is done automatically, actually, by SVD. It's just U1, which is the first left singular vector. Now, this doesn't look like a scattering profile, right? It's upside down. And that's because SVD doesn't know anything about the fact that scattering profiles are always positive. There's a sign ambiguity. So we can multiply by -1, and there's our SAXS profile. Okay. And so SVD is actually one of the features that's in RAW. So you can do this exact thing where you set a window of the data and calculate SVD. Okay. And just for fun, I tried to reconstruct the. Oh, actually, yeah, I showed you the reconstruction earlier. This is actually a Chrysol calculation from the crystal structure of BSA. And you can see it actually, and in this orange curve is the main peak from that chromatogram. So it fits pretty well, except like a teeny deviation here at mid-Q, which I think is probably actually significant and requires further investigation. Okay. The envelopes agree pretty well. Okay. So there's lots of things that can go wrong with SEC SAXS, as you might imagine. And so I'm going to go through some kind of practical troubleshooting advice that you will want to keep in mind. So one thing that can happen is you can have radiation damage. And one way that this will show up is that the protein will start to sort of stick to the windows of the sample cell and build up over time. And this is a big problem because it can compromise background subtraction. And so what I always try and do is to compare the buffer scattering at the beginning and the end of my experiment and make sure they overlay exactly. So here's an example of that. So this I stuck in the SI of a paper just to sort of prove that there wasn't any what sometimes people call it capillary fouling, any issue of sticking. This sticking tends not to be a problem at chess, although with the recent upgrade, the intensity is getting higher, and so we're starting to see more damage. So just keep this in mind that it can happen. And there are ways to mitigate damage, for example, to increase the flow rate Sometimes adding an osmolyte like glycerol will help. And you get really desperate, you can attenuate the beam. Okay, so another problem that often happens is your resolution of the column is not insufficient to separate your species of interest. So these two peaks would be baseline resolved. These two are overlapping, right? So different causes are if you overload the column, that can cause peaks to broaden. If your injection volume is too large, that could be a problem. The chromatography system also has some dead volume, and that will cause peaks to be broader than you expect. And then also your protein can interact with the media in the column, and that can also distort things. So I'll just mention that there are advanced analysis methods that can separate things even if they're pretty severely overlapping. And I'll talk about that later. This is an example of broadening where we're using a very, very small volume column, and the UV peak is much narrower than the SAXS peak, and that's because between the UV cell and the SAXS cell, it had to travel through some tubing, and that broadened the peak out. And okay, another thing, so I showed you that RG plot before, and the ideal situation is where you have a nice flat RG, right? But often that's not what you see. These are, remember that there are concentration-dependent effects in SAXS. And in this, as your peak comes out, the protein concentration is changing. So when you have a lower RG at high concentration, that means you have a repulsive interparticle interaction, potentially. And so ways that you can deal with this, you may want to lower the sample concentration, or in some cases, this is just caused by having a highly charged protein, and so adding some salt to the buffer can help. This case of frowning, so now we have RG is higher at the peak than at the end. This could be caused by aggregation post-column, or attractive structure factor, or just some kind of, this is kind of a mysterious phenomenon, but it could be sort of, people call it stickiness. You know, sometimes proteins, so attractive structure factor is a sort of reversible aggregation. Okay, and then also weakly associating oligomers. And this is kind of the more common situation where you really don't have any, doesn't look like a single thing, you have this sloping RG. This could be exchanging oligomers, it could be highly overlapping peaks from multiple distinct species. So this is something that you want to investigate further. And so SEC-SAXS is, I should say, a pretty general technique. There aren't a lot of constraints on what you put in the running buffer, but your column manufacturer will tend to recommend certain conditions. So for these GE columns that MacCHESS has, they recommend 150 millimolar NaCl, although we've run with 0 NaCl all the way up to much higher. This is to prevent non-specific binding to the media. And then for protein stability, we often add glycerol, and just anecdotally, this seems to greatly reduce radiation damage as well. Well, for certain proteins more than others, yeah. And one thing to be aware of, though, is that glycerol increases the viscosity of your buffer, so you need to watch for back pressure. You may have to run at a slower rate. And then you also have a choice of which column to use. So I think what MacCHESS typically recommends is that you start with the small column. So they have a 5150, which is I think a 5 mil column or 3 mil column. Yeah. So this one can be run very quickly. It doesn't have the best resolution, but you can usually see kind of what you've got. MacCHESS also has a medium-sized analytical column, which is a 24 mil column. This one runs more slow, or it takes longer to run, but it also runs at a higher flow rate, or you can run it at a higher flow rate. So this can be good if your sample is prone to radiation damage. you're going to use more sample, but you're flowing it through the beam or refreshing it more quickly. So that's cool. And this one would give better resolution. And then you want to typically choose loop size and injection volume to minimize the amount of dilution that happens during the experiment. So I think for the 5150, they use a 50 or 100 microliter sample loop, and for the 10300, 100 to 500 microliter loop. Okay. And if possible, you should figure all this stuff out in your home labs if you can before you come to CHESS. Since most labs have an SEC, this is pretty easy to do. And this is really just kind of a list of, I would say, like the landmark papers in for methods, SEC SAXS methods. I guess I'm probably missing CoFlow and some more recent ones, but kind of the earliest experiments were done at the APS in 2004. And then more recently, there have been some developments in software, and in particular, BioSAXS Raw now has sort of a full suite of SEC SAXS data analysis programs. Okay, and we're coming up to part 3, which is sort of my little pet project case study, but I want to take more general questions first. So any questions about SEC SAXS methods, or how you guys want to do your experiments tonight or tomorrow? Happy to answer questions. Yes.
So you have a sample that you suspect exists as several different Xmers, right? So you might have monomers, dimers, trimers up to like hexamers and so on. You're expecting that to be resolved at least to some degree on your sizing column. How much overlap in your dilution peaks is acceptable? Like,
yeah,
do they have to be like absolutely distinct, or?
Yeah, so the more separation you can get, the better, obviously. So the analysis methods can deal with separation or incompletely separated peaks. Although the more overlapping they are, the more ambiguous. And it's not just the width of the peak, it's also the width of the amount of tailing that happens at the end of the peak. So I would say it's worth spending time getting better separation on the chromatography system as opposed to trying to analyze ambiguous data.
I only bring that up because the last person that talked, Tom, he talked about deliberately, putting in different ratios of, dimer and a hexamer, and then getting, kind of these hybrid models in between them. I mean, can you also do that with the SEC stuff?
Yeah, you can, but you have to keep in mind that, like I said, if you have one scattering profile, I mean, even though you have lots of scattering profiles, you're still, I mean, you could theoretically try and sort of stay to one end of the scattering of the elution profile, and then see how it varies across the elution profile, and do this sort of mixture modeling to see if you get these volume fractions, because that can help you sort of know
so
for
I mean,
sure
if you start out on your hexamer side of the, the profile, then go all the way out to your monomer one, like, wouldn't you expect to get a kind of
change in the volume
gradient
fractions
in shape moving from one to the other?
Yeah, you should. So, but you don't necessarily want to do that because it's, it's ambiguous. I mean, if you have to, you can, but number one, separate them.
Right.
So,
yeah,
but
that's where the evolving factor analysis is very, very useful.
Yes. So in this next part of the talk, I'll mention this evolving factor analysis, which is sort of like an extension of SVD that lets us really pull out distinct profiles even when the peaks are overlapping. But as you mentioned, you could just say you don't really care about separating the individual things, and you're just going to rely on reconstructing a mixture. But I think it's always better to try and get clean, unambiguous data if we can.
I'm just worried that's what my data is going to be based on
this
run, and I don't live here, so I'm just curious what I can pull out of it.
No, yeah, I think that's true. I think often it's very hard to separate like things that are closely spaced in molecular weight. Although, okay, so this project was a collaboration between Nozomi Ando's lab, which is where I'm a postdoc at Princeton, and that of Paul Fitzpatrick, who's he's an enzymologist at UT Health and Science in San Antonio. Phenylalanine, as many of you know, is an essential amino acid. We have to digest phenylalanine. It's really critical to our health. This occurs in the liver, and if you aren't able to do this, it leads to a disease called phenylketonuria, which is one of the most common genetic diseases that all newborns were screened for. And you may have seen, like on a can of Diet Coke, it says "danger, contains phenylalanine." So that's because aspartame, which is this artificial sweetener, gets broken down into phenylalanine. Okay, so phenylalanine is synthesized by bacteria and plants. We actually don't have the ability to synthesize phenylalanine, so we have to get it from our diet. And as I said, oops, thought there was an animation. Anyway, it's broken down in the liver to tyrosine, which is then used to make neurotransmitters such as dopamine. Of course, is very important. And the enzyme in your liver that does this regulation of how much phenylalanine is digested to tyrosine is called phenylalanine hydroxylase. And normally this enzyme is off, but when you eat food, your blood concentration of phenylalanine goes up, and the enzyme turns on, makes tyrosine. This project was really trying to figure out how the regulation of phenylalanine hydroxylase activity works, and we knew that there was some allostery involved. No one had ever been able to get the structures of the inactive and active conformations by crystallography. So one question we asked first was, what does the inactive pH look like? And we were really lucky. It turned out that our group and also another group around the same time were able to solve the structure of the inactive pH. So this is with X-ray crystallography and to modest resolution. And I'm just going to give you a quick tour of the structure so you know what domains I'm talking about. So pH monomer has 3 domains. It has an N-terminal regulatory domain and catalytic domain, which is where all the catalytic residues are located, and then a tetramerization domain. This regulatory domain is part of a recently discovered family called the ACT domain. It's a recently discovered regulatory motif. And it has an N-terminal tail that extends across the active site. So this catalytic domain was known to bind pterin, which is a cofactor, oxygen, molecular iron, and the substrate phenylalanine. And the regulatory domain was thought to bind phenylalanine, although there's sort of different evidence for this. So the actual pH is a tetramer, and the tetramerization domain forms a coiled coil. The catalytic domains are arranged around the outside, and the regulatory domains sit on the top and the bottom at the interface between the catalytic domain dimers. So the interesting thing is that these ACT domains are far apart from each other in this inactive conformation. And this is what we know from other structures that include ACT domains, is that they often associate as dimers. So this was kind of a mystery. The N-terminal tail, as I said, extends across the active site, and it's thought to block access to the active site, and that's probably the mechanism of inhibition. Okay, so the next question was, what does the active pH look like? So we couldn't get crystal structures of the active pH, despite, I think, 30 years of trying. So we turned to SAXS. So as I hope you're convinced now, it's a really powerful technique for looking at things in solution. And you can get structures. Okay, so the first thing we did is we took pH and we put it just using regular, I guess what we're calling batch mode SAXS now. And we titrated in phenylalanine and tried to see if there was a conformation change or evidence of a conformation change. So what you see is that physiological phenylalanine ranges, which is about 0 to 1 millimolar, you see a small change in the mid-Q regime. And as you go to much higher non-physiological phenylalanine concentrations, you start to see an increase in I0, which is evidence of higher molecular weight species. So here is now the same data, but I'm showing it as a Kratky plot. This is to emphasize the mid-Q change. So you often see in papers about conformational changes that are subtle, they'll tend to present data as Kratky plots just because it's much clearer. So as we add the phenylalanine, you see the occurrence of what looks like a second peak in the Kratky plot. And changes in mid-Q scattering such as this are often consistent with a domain rearrangement. Okay, and the other great thing about this, so doing SVD, we can actually pull out, in fact, this is a two-state transition, we can fit it with a Hill equation and get cooperativity. So we have a n value of 2, which will become important later when I talk about mechanism. We also looked at some mutants. So this is often a good way to try and work out what's happening is you have a hypothesis and you do a mutation and you see the effect using SAXS. Okay, so this was an active site mutation. So this knocks out binding of phenylalanine to the active site. And you see the same cooperative activation still occurs. So that means that pH is not binding, or sorry, phenylalanine is not involved, not binding the active site in this activation. And you still get a cooperative transition. Okay, now if we delete the N-terminal tail, again, you still see activation. And however, this now is the deletion mutant, which is shown as the white circles. The sort of the amount of phenylalanine you need for half activation is shifted toward lower values. So that means that that tail was probably stabilizing the inactive conformation. So that means the tail probably unbinds during activation, which would be consistent with the mechanism of inhibition. Okay. Okay, so the next thing we did was we turned to SEC SAXS. Because the big question was whether, we knew that there was some aggregation occurring when we added phenylalanine, and so we suspected, from looking at Guigné plots and other things that we were not monodispersed enough to do modeling. And so SEC was really important. So this is now the plot of RG across the elution peak, and you see that at the beginning of the peak there is definitely some aggregate there. And so, we can do singular value decomposition, and we see, 3 singular values. So I've kind of walked through this before, but I didn't show what these actual columns of these matrices look like. They don't actually look like SAXS profiles. They look kind of crazy. They tend to oscillate around 0 because they're basically sort of minimal basis states to represent the data. But linear combinations of these things should be realistic SAXS profiles of the individual components. And so the question is, how do you pull those out? And the technique we developed for SAXS is actually borrowed from earlier chromatographic technique that was applied to absorption. It was like a what do they call it? Chemometrics. It's kind of an old field, but basically it's not using SAXS, but it's coupling other techniques to chromatography that have multiple observables. Okay, anyway, what you do is you do singular value decomposition for different slices of the data. And what you do is you start just at t equals 0, and you add t equals 1, you do SVD. So you get basically no singular values. You keep adding more and more data to that matrix. At some point, a significant singular value jumps out of the noise. That's what's shown here. So around frame 150, you have the emergence of the first significant singular value. And that's, when that aggregate starts to elute. Then at frame maybe 160, you have a second singular value jump out of the noise. And then finally, toward the end, you have the third one. And then what you do is you do this in the reverse direction. So you start with, t equals 30 minutes, and you add, backwards in time. And so these inflection points tell you when a species leaves the X-ray beam. And what you can do is use the first in, first out principle and say, this blue inflection point I match to this inflection point leaving, this one matches with that one, this one matches on the far right. And from that, you can say what your peak ranges are. And it turns out that just knowing the peak ranges are enough information to find the linear combinations of the basis vectors to get real SAXS profiles for the components. And this is what the components look like. So blue is now the separated aggregate component, and red is the separated tetramer. And each one has a corresponding SAXS profile. Okay, so now that we have this sort of higher quality data, we started to do some modeling. And this is the crystal structure of the inactive tetramer. And this is the SAXS data that we had for 0 millimolar phenylalanine. What you can see is that the Kristall prediction, which is in solid line here, is pretty close, but not exact. And in particular, it deviates a little bit in this mid-Q regime that we're particularly interested in for the conformation change. So we needed to actually modify this structure in order to fit the data. What we found we actually used Coral, which is a way of doing rigid body modeling with flexible linkers. Oh yeah, this is to explain what we did for the linkers. So we knew from the crystal structure asymmetry actually that one of the linkers between the tetramerization domain and the catalytic domain could adopt multiple conformations, and so that seemed like a possible hinge. So we introduced that into the modeling. If you allow that catalytic domain to open up by pivoting around that hinge, it actually is a much better fit to the SAXS data. This is now showing the black curve. Okay.
So in the model, you move it by changing some distances?
Yeah, so what the program did is it generated sort of lots of different models that were possible, given that the domains might run into each other and that the linkers had to be a certain length. And then it selected the one that gave the best fit to the data.
I see. So it was the program did it for you.
Yes. Yeah, I just set it up and then ran the program and said this was the best one. Okay, so this is now when we've added the 1 millimolar phenylalanine. Remember that that state has a sort of second peak in the Kraken plot at mid-Q. And this is showing, again, the crystal structure, which doesn't have that peak. Now, how do we model the active conformation? Well, here we're bringing in knowledge that we had separately, which is that they knew from NMR of the truncated ACT domain that it forms a dimer like this in solution, which is very similar to the ACT domain dimer of an enzyme called prephenate dehydratase, which is a bacterial enzyme that's allosterically regulated by phenylalanine. So we could build a sort of homology model in which the ACT domains from separate sides of the tetramer came together and formed dimers. And that's what's shown here. So if you take these ACT domains and you rotate them by almost 100 or 90 degrees to form this dimer, and then just calculate the scattering curve, what you see is that indeed you get the second peak in the Kraken plot. So no fitting was done in this. This was just testing a hypothesis. And we felt this was pretty good evidence. Okay. The other thing that we can do is we can build a sort of equilibrium model of how allosteric regulation must work. So we knew from ITC in this case that 2 phenylalanines bound per ACT domain dimer. So that's shown here. And this is the sort of equilibrium fraction of activated enzyme you would get as a function of phenylalanine concentration. What you'll notice is this exponent of 2. That fits very well with the Hill coefficient of 2 that I showed earlier from our titration data. So that gave us additional confidence that this was the right mechanism. And just to sort of back up, sort of big picture, what we learned is that, I said that actamains, or I mentioned this PDT, right, which is a bacterial enzyme. So actamains are actually really common in bacteria and plants, and in particular, this is the shikimate pathway for phenylalanine biosynthesis. Each enzyme that's regulated by actamains is highlighted in red, so there's quite a few. And now we know that actamains also regulate phenylalanine digestion in liver, which is kind of cool. So it's this sort of mechanism that was common in biosynthesis in bacteria and plants, which is also active in humans. This is a sort of recent picture of the Ando lab, and these folks in Fitzpatrick lab also helped. And I just want to thank MacCHESS and also sources of funding. And I want to point out, so if you want to read more about phenylalanine hydroxylase and the EFA method, both of them are discussed in this JAX paper, which came out a couple years ago. And we also have a recent review article. This article is really extensive if you're interested in both theory of small angle scattering and in applications to allostery and flexible multi-domain proteins, things like that. So I recommend this for allostery nerds. And great, so I can take any more questions that you have now. I think we have a little time.
So just from the experimental point of view, so you ran the SAXS buffer contained phenylalanine, I assume. Yeah. So one of the effects of higher concentration, like, I think you mentioned a few different concentrations before. Is one in, or is it goes crazy at 5 millimolar or 10 millimolar? What happens?
Yeah, we're not entirely sure what those high molecular weight species are. I mean, we could guess that they might be actomains from different tetramers cross-linking, but yeah, we don't know. It's a good question.
You had mentioned that PKU is a genetic disorder.
Yes.
Does that happen to be mapped back to a mutation somewhere in the actin?
Oh yeah, that's a great question. Actually, what's perhaps odd about PKU is that there are many different mutations, hundreds, that can lead to the disease, and they're spread over the entire protein. So this has been a challenge for people wanting to do drug design, for example. You don't really know. I mean, in retrospect, it's not surprising because there's such large conformational changes involved in regulation. You might expect that mutations all over the place could have an effect on that equilibrium. And then there's also issues of protein stability and folding and things like that that are affected. But yeah, I mean, that's a challenge. We're actually looking at different, I mean, one of the mutations I showed was actually a PKU causing mutation, and we're looking at other ones now. Yes.
For this particular project, how many synchrotron trips you made?
Well, for the data that ended up in the paper, that was probably maybe 3 synchrotron trips. Plus, actually, we got quite lucky in it. So we went through multiple review cycles, as you do, and a reviewer requested additional data. And it just turned out that we were able to get beam time at the last minute. We were able to go and collect the data, and we turned it around in just like a few weeks. So sometimes you can do stuff like that. But yeah, that was multiple trips. And then there was also plenty of trips collecting data that didn't end up in the paper because of data quality problems. And with mammalian enzymes, there's always issues of protein stability and preps not being reproducible and things like that. So we yeah.
Just one question. How you come about to figure out that PDT was very close to ACT?
Oh, yeah.
It's you're doing
separate tests in another lab, or that's something that it's common? I don't know.
Well, so that was partly, so our collaborator, Paul Fitzpatrick, his lab had done NMR, and they knew that the NMR wasn't sufficient to solve the structure, but they knew from, I guess, comparing the NMR with other, I'm not entirely sure how they did it actually, but anyway, the idea was they were able to map certain residues onto the structure of PET, which was known from crystallography. So, but then also, in retrospect, you can align the sequences, and it's clear that the binding residues in PET are conserved in
Correct, but it's just like you need like that previous knowledge to recognize that.
yeah, that's right. So that was lucky anyway.
That's cool. Yeah.
So I have a question about SEXAX as well. So you briefly managed the Emery-Brooks program, Ensemble.
Yes.
And then also I haven't really gotten into the BioSAXS yet. So what are the differences in these methods? Because I mean, they all sort of do the same thing, right?
Kind of, yeah.
With SVD, and so what are the differences then?
So, right. So BioSAXS raw implements EFA, which is the method that I showed.
Okay.
And EFA is kind of the most, there aren't a lot of assumptions going in. So you don't have to assume that you have a linear Guignay, you don't have to assume other things. Emery-Brooks' program assumes that peaks have a sort of Gaussian shape. So he fits Gaussians to the elution peaks. And then there's another program which I'm blanking on the name of that uses the Guignay. Yeah.
Andrew Malaby or something like that,
Right.
which assumes a linear Guignay, which is not always a good assumption. Obviously, the right answer is that raw doesn't perfectly.
Yes. I recommend. Well, you'll actually get to play with some of the data in the phenylalanine paper tomorrow during the tutorial, and you'll get to try EFA out. Yeah. And BioSAXS raw is probably I would say the easiest method to use. USSOMO is a little challenging software. So
I remember a few years ago you guys tried to incorporate the SOMO into the.
I think that was that one, but yeah. It's Emery-Brooks writes programs that Emery-Brooks can use. He's very good and he's very smart, but that doesn't mean that anyone else can necessarily.
So on the record, by the way. Thanks.
If there are no further questions for Steve, we have a chance to get a little bit ahead in time, which might be nice. So let's take a 20-minute break and reconvene at 3:45. And then we'll hear Michelle's talk. And I believe someone brought in fresh cookies over by the coffee machine. So.
That's funny.
Learn that Coral something that you use.
Now I want to.
Yeah, so Coral is one of the standard ADSAS programs, and it's been around a long time. So you can find a lot of examples in literature.
Oh, yeah? Okay. I wasn't there. I've been.
I mean, Coral is run from the command line. There's no